Hello. We are continuing our work with quadratics, and then in this section we're going to start to look at the graphs of them. So how would we plot these sort of quadratics visually? And so you should remember a general with a graph for any general function f of x. Remember I looked at functions last time. But the x values or our inputs, or you should remember the domain is on the x-axis here, and the y-axis is this line there, which is the output, right? Or the range, okay. And so a function could look like this, for example. So it's basically for every input, this graph, right, is telling us what the range is with the what input and the output corresponds to, right? So say for example we had 5 here, and then this was 30. That's telling you this point here is when x is 5, y is 30. And the beauty of the graph, it tells you every single point, right? Um, and so that allows you to visualize what the graph would look like and the behavior of it and stuff like that. Anyway, so that's a general function. Again, you should be quite familiar with that from GCSE. But we're going to look at quadratic graphs. So graphs when we have y, specifically, is ax squared plus bx plus c. Okay. And you should also remember from GCSE that a general quadratic, if we plot, the axis xy axis, it's gonna look like this, right? So it's gonna be like a sort of U shape, a smile, sort of shape, okay? And specifically, this is the graph y is x squared, okay? Um, Although hang on, it's a little bit. There we go, it's a little bit better, okay? Um, and so yeah, that's generally the shape of a quadratic, right? It has this sort of like smile shape or like a stretched U shape or something like that, right? So it's kind of like almost like a roller coaster, right? So it's going down, then up, right? And that's generally the shape you need to recognize when you draw these graphs. That's sort of what you need to remember what a quadratic would look like. Okay. And so actually, when we start to look at this sort of shape, you can either have two versions of quadratic, right? So you can have this sort of smile shape, which will look like this, right? Or you could go the opposite way, or you could instead get a sort of the opposite, the opposite, right? So it's like a frown instead. Um, so instead of going up, down, and up, like the left graph, it instead going up then down instead of down and up. Okay, and so it resembles a sort of like frown shape. So you remember, like, so this looks like a smile, right? This looks like a frown. Um, and so that's helpful because how would you determine which because any quadratic will have one of these two sort of shapes, right? This sort of the sort of structure, the way it looks. And it's to do with the sign of x squared of ax squared to the coefficient of a. So if a is positive, then it's going to have a positive sort of shape. So it's going to be like a smile, right? So smile, happy, positive. So that means the coefficient a is positive. So for example, if we had y is x squared, or 2x squared, should I say, or something like that, plus 6x minus 5. It doesn't matter what these two terms are. We only care about the x squared coefficient. And here we have 2. And 2 is positive 2, so it would be a smiley shape like that. Alternatively then, if it has a frowny shape, then a is actually less than 0, so it's negative. So for example, if y was minus x squared minus 3x, add 7 for instance, I have a negative here, so it has to be a frowny shape, okay? Again, it's frowny, sad, negative. So yeah, that's a helpful way to remember it. Okay. So that's the general shape, but there's some key details. And actually, the first one I want to look at is actually notice Let's go with the positive shape here. Well, notice when it's the kind of like when it starts to go down and then go back up. Well, actually, it reaches a minimum point, doesn't it? It's the how far below, how far down it keeps going, and so when it reaches this point here, it reaches its minimum before it shoots back up. And so, actually, this sort of point is a special point called a turning point. Okay, so it's basically like the turning point. Like think about it, not real life. It's that it's reached its turning point. It means like it's reached its limit, right? It's reached its smallest or its greatest point. Okay. So the point where it starts to turn back around. So in this case, it's going down, and then it's reached a turning point, and so then it's going back up. Okay. Kind of like a roller coaster again. But that's a specific kind of point that you need to be aware of the turning point. And also the frowny shape has a minimum point as well, right? A minimum point, so a turning point, which is here. Um, so hopefully you recognise, right, the idea of turning points. But actually, more specifically, we can be a bit more specific with this. Again, let's take our positive case here. Well, this is actually specifically a minimum point in this case. If you think about the graph here again, that is the minimum y value, right? That's the smallest y value you get from the curve, right, from the function. Um, so when you have a positive shape, like again like this, the turning point is the minimum point. It's when you plug in any value of x into that. Again, value of x into here, ax squared would be x plus c, which is what you're plotting. Any value of x, the smallest possible value of y you get out of that is at this point here, which is the minimum point. And hopefully you can see that right. Um, its dip is there. It's dip in there, so it has to be a minimum. Alternatively, again, when you have a curve a negative, right, and the curve is going down, it has a turning point, as we just discussed, but it's a maximum this time, instead of a minimum. And the easiest way, well, the way to see that is well, it's instead of going down then up like the positive curve, is going up then down. Okay, so it's reaching a highest point. Okay, and so this highest point is the maximum point. So hopefully you can see here with this graph that I circled there. It's going up and up and up until it reaches its top point, and then it goes back down. Okay, and that is what we call the maximum point. Okay, so they're both turning points, right? Because the whole idea is it's flipping direction. So it's going. So for the positive case, again, it's going down and up. So it's changing sort of course, right? And so the turning point is that point where it changes course. But the maximum point in the other direction was still turning point, but instead of going down and up, it's going up and down. So it's still changing course at this point here, but in opposite directions. But it's still changing course, right? Um, so they're both turning points because of that sort of nature, but they're different types of turning points. So this one is a minimum again because that's the minimum value of the function. That's the minimum point. That's the minimum value. That's how far. That's the furthest the curve dips, right? Whereas here it's a maximum because that's the highest the curve goes up. It's the highest point it reaches. Okay, so one's the smallest point it reaches. The other one's the highest. Okay. But we'll look at more of that later on in the course. Particularly when you look at differentiation. But I want to go over that now. Because we can actually study this in more detail with the knowledge we have. So, every quadratic will have a turning point, obviously, because every quadratic will either have a sort of a smile shape. Remember, if the coefficient of x squared is positive, or a frowny shape when the coefficient of x squared is negative. So we have one of these two shapes, but both of these shapes have a turning point, right? So we know every quadratic will have a turning point, but it will either have a minimum or maximum depending on the shape, right? But we can actually work out the actual coordinate of this by using completing the square, which we studied earlier, which is why completing the square can be useful. Okay, so let's have a look at an example of this. So, for example, find the coordinate of the turning point of the following graphs. So we have y is x squared and 2x minus 6. We don't. It's not asking us to know everything about the graph, but we can deduce the general shape of it first of all. So, for example, so we have x squared plus 2x minus 6. Well, the x squared, right? It's positive, right? It's a positive 1 uh, with a coefficient of x squared. So as it's positive, it's going to have this sort of shape, isn't it? So the turning point at the bottom here is going to be a minimum because that's how far. That's when the graph dips to the lowest point. Okay, so it has a lowest point, so it's a minimum. But how do we work out the actual coordinate? What the point is? Well, complete the square. So let's just complete the square firstly. So x squared plus 2x minus 6. Well, it's going to be x and then half of 2, which is plus 1. All squared. Then we're going to do minus 1 squared, so that's minus 1, and then we have a minus 6 at the end. That's going to go to x plus 1 squared minus 7. Now that's in completed square form. Okay, so minimum then. So this all stems from, and we did actually look at this when we looked at complete the square, looked at a few examples in this sort of this sort of idea. But the whole idea, right, is the fact that we have a square number, okay? And a square number always has to be greater than, it has to be at least 0, right? So it has to be not negative. Um, but x can we can plug in many infinitely many values of x, right? But because x is in this bracket, right? It doesn't matter if x is negative, if x is 0, if x is infinity, if x is a really large positive number, really large negative. Absolutely any value of x, it does not matter because it's all squared, okay, at the end of the day. And then that means we have a square number, which means it has to be positive, okay? It has to be at least 0, which is why we get this sort of inequality, right? This square bit, this bracket of the square has to be at least 0. So that's telling you sort of like a lower bound, right? It's the smallest, it's the smallest possible case, right? Which is 0, and then it could be higher than that. Okay, so the whole bracket bit has to be at least 0. But then we have minus 7 at the end of it. So actually, we just subtract 7 to this. So if the square number is at least 0, but no matter what, we're taking away 7 afterwards. Overall, it's going to be at least minus 7, isn't it? And so then the minimum value. So what this is saying is it has to be minus 7, but it all could be anything bigger than minus 7. But it cannot be less than minus 7 because of the whole idea again, because we have a square bracket here. So it cannot exceed, it cannot be below 0, right? So therefore the whole expression cannot be less than minus 7. Therefore, minus 7 is actually the minimum value. Okay. Actually, I'm going to write that down here to make room for the next question. So the minimum value, minus 7. But as a coordinate, well, y is equal to this whole thing here, isn't it? Remember, y was this x squared plus 2x minus 6. But I wrote this in complete square form. These are exactly the same expressions. So that if I find the minimum value of the whole expression, which is minus 7, that's also the minimum value of y because it's equal to the expression. So actually, the y coordinate is going to also be minus 7. That's the y value of the minimum point. Okay. Then to find the x coordinate, well, you may think perhaps we could sub in -7 in for y and then solve it. But actually, it's a far, far, far easier thing to observe. And that is, well, when it's -7, the minimum value, but that's when this bracket has to be 0. Because remember, the square bracket, the square, has to be 0 or higher. So then the smallest possibility of that bracket is when it's 0, right? Well, when the bracket equals 0, that means x plus 1 has to equal 0. So when it hits the minimum at -7, then the bracket part containing x has to be 0 for then the whole square number to be 0. So then x then would be -1, and that's your x coordinate. Therefore, the turning point, or TP, is -1 and -7. Okay, so that's just an explanation, but in general, then, once you've hopefully understood that part, well, then you could jump in really quickly and say, well, actually, the bracket has to be 0, so that means the x value has to be when the bracket equals 0, which we've done here. So solve that sort of equation. So when you set the bracket to 0, well, x has to be -1, such that -1 add 1 gets us 0. Then, when the whole bracket's 0, and then the minimum y value is just a number at the end, it's -7, which is what we've got there. And so therefore we can very quickly obtain the turning point once you complete the square. Okay, let's have a look at this another example then. So we have y is -3x squared as 7x plus 6. So we have a minus coefficient, so it's going to be a frowny shape. And so that means the turning point here is going to be a maximum because it's the highest point. Um, so therefore we want to find the maximum point, or the turning point. And again, how are we going to work that out? Let's complete the square. So I'm going to factor up -3 because I just want x squared. I don't want -3x squared. So I factor -3 out, x squared, and then -7 over 3x, right? Hopefully you can see that. Because then -3 times -7 over 3 positive 7, which is what we want. And then add add 6 at the end. Okay, remember we did loads of examples to complete the square earlier on. If you need to check that video out, it will be there. But yeah, this will complete the square. But then I can complete the square right inside here now, inside this bracket. So it's going to be -3 lots of xz, and then half of 7 over 3 is going to be -7 over 6. Okay, and that'd be all squared. Then I'm gonna do minus the square of that number of -7 over 6. But hopefully you recognise -7 over 6 all squared. That's going to be 49 over 36. Okay. Plus 6. Again, you put that in your calculator. You don't get too bogged down in the arithmetic. Okay. Then I'm going to bring out the minus. I'm going to times -3 to expand the bracket. So I'm going to get -3 lots of x -7 over 6 all squared. Then I'm going to times -3 with -49 over 36. And that's going to get me 49 over 12. Positive 49 over 12. Add 6. Then I'm going to bring the numbers together to get -3 x -7 over 6 all squared. And then add 49 over 12. Add 6. Gets me 121 over 12. Okay, you can do that on a calculator. Remember, you will have a calculator in your exam. But yeah, so that's completing the square form, right? So we complete the square on it. So now we need a turning point. So the coordinate, the maximum point here. Okay. Well, I can very easily spot that happens when the bracket has to be 0 because the square number has to square, so it has to be at least 0. So 0 is the minimum possibility of the bracket. Uh, so when the bracket's 0, then x -7 over 6 is 0. Therefore, x is equal to 7 over 6. Okay. Then the minimum point, well, it's just going to be the number outside, isn't it? So then y, because when the whole bracket's 0, basically this whole bit goes away, so you're left with this value at the end. So then the y point, the y value for the y coordinate for the point is just simply 121 over 12. Therefore, the turning point is going to equal 7 over 6. Oh, 121 over 12. And there we are. So hopefully you realise we can actually get it quite quickly then. If you just set the bracket to 0, you get the x coordinate, then the value, the number outside the whole bracket thing will then give you the y point. Therefore, you got the whole turning point. Okay, so that's how we can use completing squares to find the turning point, or to find the minimum and maximum values and stuff like that. Okay, now we're going to look at some examples then of the whole thing. So we looked at the shape of the graph. So again, if it's a smiley shape or a frowny shape, again, that's with a is greater than 0, a is less than 0, if it's positive or negative. We looked at the turning point, so when it's a minimum or a maximum. We saw how to use the complete square to find those points. But there's some other stuff we need to be aware of with sketching. And actually, it's, for example, here, again, if you have x and y axis, for example, here, well, this is the turning point. Cool. We know it's a smile, so it has to be positive a, the coefficient of x squared. But also with the graph, it's going to have intersections with the x and the y axis. Okay. That's what else we can work out. So we can find the coordinates of the turning point. Cool. But we can also find the points where the graph crosses the x and the y axis. Okay, that's all the information we can get, right? That's the valuable information. So once we've got all that information together, we can get a really good picture for exactly what the graph will look like. Okay, without having to literally just substitute every single point in from negative infinity to infinity for every value of x to get a precise value of y. We don't have to do that. We just care about the general shape and the key details, which will be the intersections with the x and the y axis and the turning point, if relevant. Okay, so let's have a look at an example then, because again, I think it's best to illustrate through an example. So let's work through this together. So we have a graph of, it's asking us to find, sorry, the graph of x squared minus 5x plus 4. Again, firstly, you need to quickly work out, well, it's a positive coefficient. It's 1, but it's positive 1 of x squared. So it's going to have a smiley shape. Then we can find the coordinates of the turning point here by completing the square. So then if we said, well, then if we complete the square on x squared minus 5x plus 4, it's going to be x minus 5 over 2, half of 5 minus 5. You get minus 5 over 2 all squared. Then I'm going to minus the square of 5 over 2. That's going to be 25 over 4. Add 4. Then that'll go to x minus 5 over 2 all squared. Then I can work out minus 25 over 4. Add 4 on the calculator, for example, and then you'd get minus 9 over 4. Cool. So that's in complete square form. Cool. So then we can find the turning point very quickly, actually, by just saying, wow, the turning point. Well, the x value is the x which makes the bracket 0, but x has to equal 5 over 2, right? Because then 5 over 2 take away 5 over 2 gets us this whole bracket equal to 0, which is what we want. Then when the bracket's equal to 0, then the y value, because y equals the whole thing, is just going to be this number outside, so it's going to be minus 9 over 4. And there we are. And I will always, always, always work in the same way every single time. Okay, when you with quadratics, when you complete the square, the turning point will be in that way every single time. So that's the turning point. Cool. Then again, we need to be a bit more specific. We need to find where the graph hits the x and the y axis when it crosses. This is just a general depiction, but we need to find the x-axis intersection and the y-axis intersection. Okay, so first let's look at the y one. Well, think about again, think about the graph on the y-axis. That's when x is 0, isn't it? Okay. So really, to find when it crosses the y-axis intersection, that's when x is 0, isn't it? So then you substitute x equals 0 into our equation. So then y, obviously the y value when it crosses the y-axis, is going to be 0 squared minus 5 lots of 0, add 4. Well, the zeros go away, so you're literally left with y is 4. Okay? Therefore, the coordinate, or the y-intercept, is going to equal, well, xy, right? But we know x is 0, and then the y value is 4. So that it crosses the y-axis then at 4 for y. Now we need to find the x-intercept. Okay, so the x-axis now, where it crosses the x-axis. Well, in the same way, on the x-axis here, that's when y is 0, isn't it? So we're going to set y as 0 this time. So then simply, then if you set y 0, that means 0 has to equal x squared minus 5x plus 4. Or we could flip that around to say x squared minus 5x plus 4 equals 0. And hopefully then you recognise this is an equation to solve, right? And we can solve that then. Okay, so what method should we use, right? There's a lot of methods we can use now. We can complete square, we can factorise, potentially. We can use the formula. But I think I'm going to factorise because we can spot 4 here. 4 and 1. If I make them both negative, I add to get minus 5 and they times to get 4. So my factors are x minus 4, x minus 1 equals 0. Remember, we spent loads of time solving quadratic equations if you need a refresher. But then two solutions, x is 4, x is 1. And those are the 2 points then where it crosses the x-axis. So here that would be minus 4 and here it would be minus 1. Oh no, sorry, 4, positive 4, positive 1. So the coordinates then, so the x-intercept, if you will, and there's 2 of them because there's 2 x values. Well, that's going to be x is 4 and a y would be 0. Remember y 0? That allows us to set the quadratic equal to 0. Or 1 and 0. Okay. And now we've got everything. We've got every ingredient. So we know it's going to have a smiley shape. Um, and the x-axis, well, it's going to cross. So if we draw a general, right, general x and y grid, it's going to cross the x-axis at 1, say here, and 4 here. It's going to cross the y-axis at 4, remember here. It's going to have a turning point of 5 over 2. Around 5 over 2 is 2.5, so it's going to be about here, right? 5 over 2. And minus 9 over 4, which should be down here somewhere. So the turning point will be there. It will cross the y-axis there, and it will intersect the x-axis there. Okay. And so actually we can write this as just simply 5 over 2 minus 9 over 4 to give the coordinate the turning point. So actually, with these 4 points are marked down, we got a very, very good idea what the graph will look like and where it goes. So if we just almost connect the point by making a U shape, we get this sort of shape here, as so. And remember, we continue on. And that's the shape, right? That is a sketch of the graph. So a sketch being a good representation of the shape of the graph and the key points that you need to be aware of. Okay, and there we are. So that's our sketch there. So yeah, so that is essentially the ingredients of sketching a quadratic. We need to establish whether it's a smiley shape or a frowny shape. We need to then establish where the turning points are, and then when the x and the y-axis intersections are by setting x is 0 and y is 0. Okay. Anyway, let's have a look at another example. So we have for y is 4x minus 2x squared minus 3. I don't like how they switched the ordering around a little bit. let's put the x squared bit first. So alternatively, that's minus 2x squared plus 4x minus 3. That's just a personal preference. I think it's a bit cleaner to read. But hopefully you recognise, well, the coefficient is negative 2. So actually it's going to have a frowny shape, okay? And so the turning point is going to be a maximum, okay? This time round. So then, firstly, how are we going to work that out? Well, we're going to find the turning point, this maximum point here. We need to complete the square. So if we complete the square, we need to factor out a minus 2. So minus 2 lots of x squared, and then minus 2, because then minus 2 times minus 2 plus 4x, and then minus 3 at the end. Then we complete the square inside the brackets. We're going to have minus 2 lots of, and then x, and then a half of minus 2 is minus 1 all squared, and then minus 1 squared is minus 1, minus 3. Oh. And so there, we can expand this, so we have minus 2 lots of x minus 1 squared, and then minus 2 times minus 1 is plus 2 minus 3. That will go to minus 2 of x minus 1 squared. 2 minus 3 is minus 1. Cool. And then quickly we can read off then that the turning point is going to be well, the bracket 0, so that means x has to be 1. So x minus 1 is 0, so x has to be 1. And then the y value, the y counterpart is going to be negative 1. Okay. So cool, we found the turning point. Then we need to establish the x and the y axis intersections. So firstly, the y-axis. So remember, if we have a curve, like the graph's going to look like this. So those are the y and the x-axis intersections. That's a very general shape, but that's what the intersections will look like. So with the y-axis intersection, first of all, it's going to be when x is 0. So corresponds to this point here. Well, when x is 0, then y is going to be, well, minus 3, isn't it? If I set 4x to be 0, 2x squared to be 0, I'm left with minus 3. Okay. So very quickly introduce y is minus 3. Therefore, the point is 0 minus 3. Okay. Then the x-axis is when y is 0. Therefore, minus 2x squared plus 4x minus 3 has to equal 0. And then we can solve. Okay. So let's use the quadratic formula. I don't know. Just to be lazy. Because I don't want to complete the square or factorize. I don't know. So xn is simply minus 4 plus the minus square root of 4 squared. Minus 4 lots of a, which would be minus 2, and then c minus 3, over 2 lots of a, so 2 lots of minus 2. So that would be then put that into your calculator. Or at this point, you can just put it into the quadratic solver function in your calculator. I went over that last time when we looked at solving quadratic equations. To save you writing down this whole ugly quadratic formula. But it's still advised to write this formula down to make you to show you're working, so you're not skipping anything. And actually, this is a good point. Actually, if you put this in your calculator, then you get this sort of, you get this. You get this in your calculator. So this is weird. 1 plus root 2 over 2i. Okay, it says I, by the way, not 1 or anything like that. And then 1 minus root 2 over 2i. Some calculators actually will say it's undefined, but smarter calculators will actually give you this I. Now, if you do further maths, you will look at this. You're looking at area equal complex numbers. But when we're specifically looking just in terms of real numbers, in normal maths, right? I essentially means it's not a solution, okay? And the reason why that happens, it's not an actual solution. It's because look at this this square root here. This square root of 4 squared minus 4 minus 2 minus 3. That that goes to um that goes to if you work that on the calculator, for example, 4 squared minus 4 minus 2 minus 3 is minus 8. But hang on a minute, you can't have a square root of a negative, okay? Because it's essentially saying it violates the idea that two negatives multiply together to get a positive. Uh, because two negatives have to multiply to get positive, but this one's saying two numbers squared times together gets a negative result, which is nonsensical. So that tells you there's no solutions. But what that means instead, if there's no solutions, that means it doesn't cross the x-axis. So instead, the graph is going to look like this. So the maximum point is not going to be crossed on the x-axis. So it's never going to touch the x-axis once, okay? So when you, in this situation, when your answer has this weird I number in it, this letter, or you have a square root, and you should check if you get a square root of a negative. Um, um, But that essentially means there's no solutions for x, which means there's no crossing with the x-axis. Okay, so therefore I'm going to deduce x in, no x intersect. Oh no, that sounds dodgy. No x-axis intersection. There we are. Um, So actually, then the only information we have is the turning point and the y intersection, the 0 minus 3. So if we piece all that together, then let's do a little graph here. So the y-axis it crosses the y-axis at -3, and the turning point is at 1 minus 1. So it's going to be about there. Okay, so if we do the -3 over here, so it's going to cross the y-axis there, here, right? And the turning point is there at 1 minus 1 there. So so really, and we discussed because it cannot cross the x-axis, so it's going to look a bit like this, right? There we are. No, hang on. There we are. So it's going to cross at -3 here. So as you can see there, in this case, the shape does not cross the x-axis here, right? Does not cross it. So therefore, you're going to get no solutions when you solve the quadratic. But we still have a turning point, and we still have a cross with the y-axis. Okay, and there we are. Okay, cool. So again, that's the procedure with sketching quadratics. We deduce the type of shape, if it's a frowny or smiley one, by looking at the coefficient of x squared. We look at the turning point by completing the square. Then we solve the y-axis. We'll set it. Solve the y-intercept. So the y-axis when x is 0. That's easy to do. Then you've solved the quadratic when you set y is 0 to get the x intersections. Okay. Okay. The other point to this, which we sketched the graph, oddly enough, the question asks us to find the equation of the line of symmetry. So the line of symmetry, again, referring back to GCSE, that is, say, well, what does our curve look like? Well, it's a Frowny shape. So if we draw a general Frowny shape, the line of symmetry is where we draw like a line, example there, and everything to the left of the line of the mirror is exactly matching the right of it. And actually, the line of symmetry for quadratic always coincides with its turning point. Again, another useful turning point. So the line of symmetry is going to be a vertical line, so that's going to be mirroring the y-axis. So it's going to be x equals something, isn't it? Because if you think about if you have a general axis here, if you have a vertical line, that's occurring for some particular x value. Okay, so it's going to be x equals something for the equation of the line of symmetry, and again, it's going to go through the turning point. So we worked out the turning point to be 1 minus 1. Therefore, line of symmetry, if we write it down here, that's going to be again, it's going to pass through essentially the turning point, and it crosses the x value of the turning point is 1, isn't it? Down here. So the line of symmetry therefore x is 1. Okay. Again, remember GCSE when we write vertical lines. Remember once again, it's x equals some number. Okay. Because it has multiple y values because it matches the y-axis. So it's only fixed for the x values. So it has to be x equals something. Okay, and then the x value, well, it's going to be where it crosses the turning point, which we discussed is when x is 1 there. So there we are. So if it asks for line of symmetry, always, it's to do with the turning point. Okay. Likewise, if it went the opposite way around, again the turning point would be there, and then it will still cross through vertically like that. So x equals the turning point. Okay, and that's the line of symmetry. Okay, cool. Let's move on. So I've got more examples then. So here we've got a past paper question. And so part A, we are given f of x is 2x squared plus 4x plus 9. First of all, it's asking us to write f of x in this form here. You should recognise that this is completing the square because I have a square bracket of x, okay? So let's complete the square. So first of all, I'm going to need to factor this 2 out of the x squared coefficient. So that's going to be 2 lots of x squared, then in half of 4 will be just 2 plus 9. Then I'm going to complete square inside the whole thing. So 2 lots of x plus a half of 2 plus 1, all squared, then take away 1 squared, which is 1, add the 9. Then that goes to 2, you're going to expand it, so we have 2 lots of x plus 1 all squared, take away 2, add 9, and so then that's going to get us 2 lots of x plus 1 all squared plus 7. There we are, we wrote it in this form here that they wanted us to do. If you match then the form they wanted uh, here, you can read off that A is 2, B we added is going to be plus 1 here, and then C, the number at the end, is going to be plus 7. Okay, you don't have to write that down, but I'm just making it very clear. Um, you know what the question's saying, right? But yeah, there we are. Cool. That's part A done. Part B then, it's asking us basically to sketch the curve, showing any points of intersection with the coordinate axis. So that's x and y. So again, any points where it crosses the x and the y axis, like here, here, and here, and the coordinates of the turning point. Well, first of all, we can do the turning point. Well, actually, first, what's the shape going to look like? Well, we have 2x squared, it's positive 2, so it's going to be a smiley shape, okay? So therefore, we're going to have a turning point that's the minimum. Okay, well, to find the turning point, again, because we complete the square, that means we essentially, to find the x, firstly the x coordinate, well, that's going to be when the bracket's 0, so it's going to be minus 1 for x to set the bracket to 0. X plus 1 is 0, so x has to be minus 1. Then the y value is to 7 at the end, so it's 7. And there we are. And to specify, that's going to be a minimum, not a maximum, because of the way the shape is is going upward like this. It's like a smiley. So it's a minimum. Okay. Then we need to, again, find the intersection of the y and the x-axis. So again, it's going to look a bit like this, perhaps. I don't know, perhaps. So these three intersections there. So again, let's do the y one first. So the y-axis first of all. That's going to be when x is 0. Because it's on the y-axis, remember. It's always when x is 0. Well then, if I set x as 0 into f of x here, well, these two, 2x squared and 4x, they cancel because they go to 0, so I'm left with just 9. And there we are, so therefore the point is going to be 0, 9. Cool. Then the x-axis. Okay. That's going to be the y0 this time. Okay. So if you're on the x-axis, remember, here, that line here is going to be specifically with y0. Okay. Anyway, so when y0, well, then 2x squared and 4x plus 9 equals 0. F of x, we call it, said y is equal to f of x. So this whole quadratic is equal to y. So then when y is 0, the quadratic set to 0. Anyway, nothing unusual there. And then we solve it, and we can again perhaps just use quadratic formula to save any bother. So x would be minus 4 plus or minus the square root of 4 squared minus 4 lots of 2, 9, all over 2 times 2. Okay, and then hopefully what you spot here is it's the same sort of issue as last time. If I were to put that in a calculator, if I were to solve this, put this in a calculator, I again get this I business. I get minus 1 plus root 14 over 2I and then and then another 1. But it's I again. Why am I getting I? Remember, if you see it in the normal math course, there's no actual solution. And that's again because of this square root. So this square root again, so you get root, root 4 squared, 4 squared minus 4 lots of 2, lots of 9, you get root minus 56, okay? And therefore we get a negative square root, so again, there's no solutions, okay, here. So no x-axis intersections, okay? So again, the graph what we're going to have, so it's going to be a smiley shape, but it must not cross the x-axis because, as we just discussed, there's no solutions when you've solved the quadratic. So if you imagine the x-axis there, it's going to have to be above it, right? Because if it's going to go in this sort of shape here, it's going to have to be above the x-axis. If it was below, well, it's going to have to cross, right? So it has to be strictly above the x-axis in this way. But exactly where? Well, we're going to use the turning point and the y-axis to find the other bits of information we need. So the turning point, if we were to do the graph here, then x and y. Well, the y-axis is going to be 0, 9. Never mind. 0, 9. So 9 is probably about there, right? It's quite high. So you have x and y. So it's going to cross there at 9. But then the turning point is minus 1, 7. So 7's going to be about there, right? And minus 1's going to be there. So the turning point is going to be there, okay? So then if you sketch the graph, it's going to look like that. I'm going to do it more clearly. Hang on. So if we draw a bigger representation, so 9 is going to be about there, then 7 is there, and then minus 1's there. So that's the turning point, and then that's the y-axis intersection. So it's going to look like that, okay? And as you can see there, it's not going to cross the x-axis. So that is our graph, okay? Cool. So hopefully you start to see a recipe of what we're going to do each time, right? We complete the square, find the turning point. You look at the you look at the shape if it's smiley or frowny by looking at the sign of the x squared coefficient. Then you find the x and the y-axis intersections by setting x and y equal to 0. Okay, cool. Okay, I'm going to get rid of this to make room for the next question. But this is the shape. Okay, hopefully you can see that. Hopefully it starts to make sense now. This should be a good refresher, a good reminder from GCSE. But you might not be used to doing all of this from GCSE, right? You do the whole shebang, right, at A level. You do the turning points, you do all the intersections, the x-axis and y-axis, and so on. So it might be a bit more in depth, but hopefully this whole idea makes sense now. And yeah, it really brings the whole chapter together, right? So how to solve equations. We looked at how to complete the square. We looked at So it's really bringing everything together, and we're mixing functions in as well, as you can see here. Anyway, look, we got this question now. So we're going to go the opposite way round with this sort of question now, and they might do this. I don't know. Test your problem solving instead of sketching. Now they're going to give us the sketch and go backwards to work out what the quadratic expression is. Notice how they just say it's ax squared plus bx plus c. We need to find the coefficients using the graph. Okay, interesting. So let's have a look at part B first. Um, Okay, so I think firstly the key idea is look at the values we're given. So we've got -2, 5, and 10, specifically when they cross the x and the y axis. Okay. So think back to earlier on in the chapter. When you have the first of all the roots, so when it crosses the x-axis, right? The solutions that the quadratic equal to 0 when we can factorize, right? So if we have the two roots x minus a, x minus b, for example, if we equal 0, then the two solutions are x is a or x is b, right? We can work backwards to if you're given the solutions here, the x solutions when it crosses the x-axis -2 and 5. So if x is -2 or x is 5, which are the two roots, again, remember roots are when f of x equals 0. So the values of x such that the curve or the quadratic equals 0. Okay, as a reminder. Well, we can work backwards. So if x is equal to -2, then x minus x plus 2, if we add -2, equals 0. Or x minus 5 equals 0. That gives us our two factors, right? Here in this all. So we can work backwards and then say, well, it's x plus 2, x minus 5 equals 0. Um, okay, cool. So then we can expand it, right? Because then if we expand it, remember factorizing, if you factorize, if you expand it, you get the original thing back. So then if you expand it, these brackets, so you're going to have x squared minus 5x, add 2x, that's going to be minus 3x, minus 10 equals 0. But that's actually a quadratic, right? Um, but it's equal to 0. But we can just ignore that because 0 specifically when it crosses the x-axis. But for the whole curve in general, we can just say that's equal to y. Okay. So the whole quadratic in general is this. Okay, cool. Okay. But then we need to have a look at this. So y is 10. But the problem is that the y-axis, that's when it comes to the y-axis, but here it's -10. So we need to adjust for that by then factoring in out a minus 1 to both to everything, right? So minus x squared, sorry, because they're minor. Oh, no, hang on. No, sorry, we need to times it by minus, right? Because that's equal to 0. I can times both sides by -1. To then get minus x squared plus 3x plus 10 equals 0. And I get the same sort of quadratic, but now I get plus 10, which is the y-axis, and actually this is our quadratic. And that makes a lot of sense, doesn't it? Because now I have a negative in front of the x squared, which means it has to be a frowny shape, and this one is a frowny shape. Whereas if we had positive x squared, that would imply the shape looks like that instead, which isn't what's happening here. So actually, that is our final result. So a general, the quadratic. So y is g of x. That means our function g of x equals minus x squared plus 3x plus 10. Cool. Um. Okay. Cool. Let's have a look at part D. Part D here. Okay. So I know it's a smiley shape. But again, I can kind of work backwards with the solutions like I did last time to get factors, which you can expand. So I have -1 and 4. So we're going to have the root x plus 1, x minus 4 equals 0, which are going to be our two factors, right? Because then obviously we set each bracket to 0, you're going to get x is -1, which is this root here, x is 4, which is going to be this root there. So we're good. So then we can work backwards and expand it to get a quadratic expression. Okay, cool. So if we expand that then, we have x squared minus 4x add x, that's going to be minus 3x, minus 4 equals 0. Okay, so we get a quadratic expression. And actually, you notice the coefficient's positive and it's a smiley shape, so we could be good. But let's check with what we have for the y-axis intersection. It's -1, but here it's -4. Interesting. That's not the same. Oh, okay. Well, why is that? Well, that's because of the fact that we actually, when we are factorizing, when you're going in the opposite direction, instead of first factorizing to get a solution, if we instead of going backwards like we're doing to get the solutions to get the factors to expand it, right? If we go in the opposite direction like we're doing, what you need to account for is the coefficient of x, a here. The coefficient of x squared, sorry. So we have ax squared, dot, 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 which should be a here. The reason for that is because, notice this is equal to 0, right? So when this is equal to 0, if I divide by a, I get the exact same factorization, and nothing changes with the roots. So to adjust for the fact that the fact that that it could be ax squared, we need to times by a number outside the bracket to adjust for the fact that there might be a multiple that would go away if I divided it by because it's equal to 0. I can divide both sides by a, and then that goes away, and then I get the factors. But I want to account for the a because in this case the y intersections aren't matching up. -4, -1. That's telling you I've not accounted for something, and that is the reason why. Okay, whenever you're working backwards, when you've got a solution and you're working backwards to get the factors to expand, you need to account for the fact there could be an a. Okay, and so then if we were to expand that, well, this is the expansion, cool, but again that's going to be multiplied by a. So then let's expand it. I'm going to get ax squared minus 3ax minus 4a equals 0. Okay. Well, to work at a, again, I have to note that the y-axis of the actual quadratic has the y-intercept has to be -1. That's telling you this number outside has to be -1. So that means -4a has to equal to -1. That means we can solve for a. So a would be -1 over -4, which should be 1 over 4. Therefore, our quadratic would be, if we sub that a in, we get a quarter x squared minus 3/4. 3a is 3 times the fourth, which is 3/4 x minus 4, well, -1. Because then -4a is -4 times a quarter, which should be -1. And again, that equals 0, but at that point, uh, because if we want the whole curve, that's just equal to the whole function, which is actually was j of x in this case. Okay. Okay, so that was a quite. That's one thing I really want to pick up on. When you're going backwards, in that case, you need to account for the fact that there would be there is a multiple you need to account for because of the fact if we were to go on to solve it to get x is -1 or x is 4, which is what we're given, you can just divide by a, like solving an equation, right? If we have ax is equal to 0, well, I can just get rid of the a, and then I get x is 0. But the fact is, there still wasn't a, right? There was still multiple. But I can cancel out multiples by dividing by it when solving. So I need to account for that missing multiple, okay? And that's a really important thing to consider. And it would make sense because, like in this case, if I were to forget that, well, I noticed something went wrong when I had an intercept, y-intercept of -4 instead of -1. So something went wrong, so that I have to account for the missing uh, multiple a, and that makes sense as well because if I just had if I just put in these two factors and not put out a multiple, I would always get x squared. But in reality, we can have a quadratic of ax squared, right? So I need to account for that a as well, which I can do that by factoring an a out. Um, like we complete the square, right? When we complete the square, we always factor the a out. So the idea of factoring out the coefficient, you just need to be aware of. Okay, but there we are. Cool. And I have seen exam questions like this, by the way. I have seen exam questions where you need to consider this a, where they give you a graph, and then you got the solutions, but you need to work backwards to get to get the function expression. But to do that, you need to factor in, oh, pun intended, that a is a multiple outside the factors. So yeah. Anyway, hopefully that made sense now, though. Yeah. Last question then. We are given the graph of ax squared plus bx plus c. It has a minimum at 5 minus 3. Well, it's a minimum, so it's going to be dipping down like this, okay? That's kind of what I expect the graph to look like. And it passes through 4, 0. Wow, that's x is 4, y is 0. Okay, that's telling us when it's 4 here on the x-axis, it's going to pass through there. Okay, find the values of a, b, and c. So a minimum at 5 minus 3, it's going to be down there. So it's going to look like that, right? Kind of, perhaps. Yes. So that's the turning point of 5 minus 3, and that's the x-axis intersection of 4, 0. Okay, it's asking us again to work backwards in a way to find the values of a, b, and c. Now this time they've not told us both the roots, so we can't just work out the two factors, right? And then expand. But what they've given us instead is actually the turning point this time round. Well, actually, we could kind of reverse engineer and work backwards with completing the square. Remember the completing the square, we have to set the bracket equal to 0. Well, the minimum is x is 5, y is minus 3. So that if the bracket's equal to 0, then if x is 5, it has to be minus 5 to counteract it to get 0. Well, then if I put the 5 in for just x, then there we are. That tells us our bracket, okay? And that makes sense because then if x is 5, then that clearly equals 0, which is what we want. And then the minimum value, the y value, is going to be the minus 3 at the end. Okay. Okay, cool. But what you also need to notice, however, is that we need to account for the a. Why? Because if I were to expand this bracket, I would get x squared plus something, some lots of x, a number, right? I don't care, but I'll just have x squared. But in reality, I need to account for the fact I have ax squared. The way to do that is to tag an a on with the bracket. Because then if I expand it and then times by a, I then get ax squared plus some lots of x. And so therefore I account for a number in front of the x squared, okay? So having a lots of x minus 5 squared. Remember that doesn't change anything because if the bracket's 0, x is still 5, but then a times 0 is still 0. And so therefore the y value will still be minus 3. Anyway, so that's completing the square. And actually, we can expand that now, can't we? So then I'm going to have a lots of x squared. Remember, x minus 5 squared is x minus 5, x minus 5. Then I could expand this bracket. So then I'm going to x squared minus 5x minus 5x minus 10x plus 25, then minus 3 at the end. Then I can times by the a, expand the bracket get ax squared minus 10ax plus 25a minus 3. Okay, and then that's going to equal to y, right? So y is going to equal this here, this expression here, and it kind of matches. I know there's loads of a's everywhere, but the point is now I have ax squared, and then have some lots of x and then a number at the end, here and here, right? But how am I going to find out A? How am I going to find these values out? Well, I'm also given a member, this point here, it goes through 4, 0. So actually, when x is 4, y 0, that's what that's telling me. Remember, I wrote it up there. I can almost substitute that in. So when y is 0, x is 4. So that means then 0 is a lots of 4 squared minus 10a lots of 4 plus 25a minus 3. If I were then to compute this in a calculator, compute this, say, calculator, that'd be 16a. 4 squared is 16 lots of a, minus 10 times 4, which is minus 40a, add 25a minus 3 equals 0. Wow, is that not an equation I could solve then for a quite nicely? Because then I can bring all the a's together, so I have 16 a's minus 40 lots of a's and 25 lots of a's. I just get a, that goes to 1 actually. So we get therefore a minus 3 zeros, so a has to equal 3. And there we are. Then I could just plug in a into here, so therefore y is ax squared, which should now be 3x squared, minus 10a lots of x, well 10 times 3 is minus 30x. And then 25 lots of 8 is going to be plus 75 minus 3 at the end. And then I could bring the numbers together to get 3x squared minus 30x plus 72. Okay, and there we are. That is our quadratic found. And therefore it's set to find the values of a, b, and c, where a is 3. And then if we read off the graph, read off what they've given us in the answer here, b is clearly going to be minus 30. Here, right, minus 30. And C would be 72. And there we are. Cool. There we are. I feel like some, no, that's it. Also, yes. So this A as well, in front of the x squared. Remember, even look at previous examples earlier on. We looked at cases where we need to factor an x out when we complete the square. For example, in part B here, remember we have a minus 3 outside the bracket here. So you can have numbers outside the bracket. And that minus 3, remember, reflects the minus 3 of the x squared. So we do need to remember, if you're working backwards to find the original equation, you need to account for that a, that coefficient of ax squared. Okay, just to remind you. Again, in this way, I have minus 2 here. That stands for minus 2 there. So if I were to work backwards, given the turning point, I'd need to tag on a minus 2. Okay. But yeah. Okay. But yeah. So hopefully you can see now. Those are quite hard examples, I think. But really just test your knowledge on this. But yeah. So that's sketching the graphs. Sketching quadratic graphs. Again, that should be a good reminder from GCSE. Although we have these last two examples were quite a step up. But hopefully when you looked at this now, it makes sense what we've done. Okay, but yeah, I will leave it there, but I shall see you next time.